Projectile motion type 1. A projectile is an object moving in 2 dimensions where it only experiences an acceleration downward due to gravity. 3 types of projectile motion will be analyzed. Here, when we have a horizontal velocity and then it falls like a marble rolling off a table. Here, like a soccer ball being kicked to another player where it lands at the same height that it was kicked from. And over here, where we launch something off of a cliff at an angle. There is 0 acceleration in the horizontal direction in any of these cases, and their paths are parabolas. Projectile motion is analyzed by solving the vertical and horizontal motions separately. The speed in the x direction is constant, as there's 0 acceleration. The speed in the y direction is changing as it experiences an acceleration due to gravity. If not for gravity, projectiles would continue in a straight line, and if aimed parallel to or above the horizontal, would never hit the ground. Gravity determines how far the projectile travels, so most problems start off with solving for the time the projectile is in the air, using kinematics equations in the y direction. All projectile motion problems will be solved by resolving them into 2 separate one-dimensional problems, the x and y dimensions. Kinematics equations only work for one dimension at a time. When dealing with the x dimension, you'll use these equations, which are the versions shown on the AP1 equation sheet. However, if you're dealing with the y dimension, those vector quantities are going to all have to be in the y dimension, so you can use these versions. Projectile motion type 1 refers to projectiles that are horizontally launched off an elevated surface. For example, if a ball rolls off a table. In this case, all the initial velocity is in the x direction, and none of it is in the y direction. This is the simplest type of projectile motion problem, since the middle term of kinematics equation 2 in the y dimension goes away, because this term right here is 0. Also, all objects in free fall near Earth's surface have the same acceleration, negative 9.8 meters per second squared. So we are going to know that term as well. Example 1. A mountain lion leaps horizontally from a 7.5 meter high rock, so this height here is 7.5 meters, with a speed of 4.5 meters per second. How far from the base of the rock will the lion land? So let's say he jumps like that. We're looking for that displacement there. Analyze the givens. In the x direction, the initial velocity is 4.5 meters per second. There's 0 acceleration in the x dimension, and the initial position is we're going to say that that's 0. In the y direction, the acceleration equals negative g since the lion is in free fall. The initial velocity is 0. So look, all of this lion's initial velocity is horizontal. There's none up or down, right? So it has 0 initial velocity in the y direction. And the initial position is 7.5. Since ground is going to be 0, that's 7.5 meters. As the lion falls vertically, his vertical speed will increase. However, due to 0 acceleration in the x direction, the lion's horizontal speed remains constant. Many times, drawing a sketch and adding the givens is helpful. It doesn't have to be as artistic as this one. Here, we're translating the givens in the problem into math variables. You might be wondering, wow, look, there's only 2 numbers in this question. How are there so many variables here? But these are all of the possible variables. And look, if we go through them, we're saying our initial position was 0. We want to find out how far we go. So that's a question mark. We're trying to solve for that. We know our initial velocity in the x dimension is 4.5 meters per second. That's one of our numbers up here. We also know there's no acceleration in the x dimension. There's no forces pulling the lion left or right. As you know, over here we have gravity pulling down. Over here there's no forces pulling left or right, therefore there's no acceleration. And therefore, the final velocity in the x dimension will still be 4.5 meters per second. So as this lion jumps, there's still going to be that constant horizontal velocity of 4.5 meters per second. In the y dimension, we start up at a height of 7.5 meters. We land at a height of 0. Our initial velocity in the y dimension is 0, since all of that velocity is horizontal in the x dimension. We don't know the final y velocity. We could always solve for that. We don't know how long the line's in the air. And we do know that since this line's in free fall, the gravity will be the acceleration due to, well, the acceleration will be gravity on Earth, which is negative 9.8 meters per second squared. Time is the only variable that both dimensions have in common, and it will always be the piece that connects them. Since we know initial y, the velocity in the y dimension initially, and acceleration in the y dimension, we can use the second kinematics equation in the y direction to find time. Time is the only unknown in this equation. So let's solve the equation for t, for time, and then substitute in the givens, and we see that that negative sign cancels with that one. This means that the lion is in the air for 1.24 seconds. Now that we have the amount of time the lion's in the air, add it to the list of givens. Look, it's here on both sides. Even though we're working in 2 dimensions, the time that the lion hits the ground is the same for both dimensions. There's only one lion. Now, the only missing variable that we're looking for is the distance traveled, x, right? We're trying to find how far from the base of the rock the lion lands. Now that we have time, we can use the second kinematics equation in the x dimension to solve for x. So here we have it here, and you can say that we're going to start the leap at a position of 0, and we're trying to find the final position. There's no acceleration in the x dimension, so this whole term goes away, leaving us with x equals v naught t. Now the initial velocity in the x dimension is 4.5 meters per second, and the lion is in the air for 1.24 seconds. So if you're traveling at 4.5 meters per second for 1.24 seconds, how far do you go? 5.6 meters.